Right, I'm back, and today we're going to be talking about graphing rational functions. A rational function can be written in this form: f of x equals polynomial divided by another polynomial. Now remember, a polynomial is any monomial or the sum of difference of two or more monomials. A very key thing when we're dealing with rational functions is the value of the variable cannot make the denominator equal to 0. Because remember, if you try to divide something by 0, like 7 divided by 0, that's undefined, cannot be done. Okay, so we cannot make the denominator equal to 0. So we're going to go ahead and try practice the graphing a rational function. This one is a word problem. You are going on a 12-mile bike trip. The function t equals 12 divided by r models the time in hours that will take you to travel 12 miles at different rates of speed. And we're going to graph this function. The first thing you'll probably want to do is settle on a good scale. And because this is in the form t equals something, I'm going to put time on my y-axis and the rates on my x-axis. And I'll just go ahead and count up by ones for a scale. So go ahead and choose a good scale, label your graph, and I could go farther, but I'm going to stop at 12. So one thing you're going to notice is you cannot have the denominator equal 0 in this case. If the rate is 0, you're never going to finish the 12-mile bike race. So the time is not going to happen. You're not going to be able to figure this out. Just like graphing any other function, though, it's totally fine to use a table. And I'm going to try to pick some nice convenient values for r, like 1, 2, 3, 4, 6, 12. I chose factors of 12 because that would make me a nice, pretty whole number answer when I divide it out. So 12 divided by 1 is 12, 12 divided by 2 is 6, 12 divided by 3 is 4, 12 divided by 4 is 3, 12 divided by 6 is 2, and 12 divided by 12 is 1. So then I'm going to go ahead and plot these points. 1, 12, 2, 6, 3, 4, 4, 3, 6, 2, 12, 1. And this actually should remind you of a graph we've done before because this is an inverse variation, and we're going to plot the points with a smooth curve. Notice it's going to kind of keep going, but it's never going to hit that y-axis or that x-axis for that matter. Okay, you notice when I said it never hits that y-axis or the x-axis in the last one, those are called asymptotes. Asymptotes is a line that a graph of a function gets closer and closer and closer to, but it never actually reaches. So this first graph on our left here says y equals 1 over x, and you're going to notice that this vertical line and this horizontal line, those are called asymptotes because the graph gets closer and closer and closer to it, but it never actually reaches it. And the reason why that happens is because in this case, if that denominator, if x equals 0, that's not going to work. So x can't equal 0, so you can never make that hit. And then in the second equation, y equals 1 over the quantity x minus 2. If x minus 2 were to equal 0, we know we can't make that equal 0. So if we add 2 to both sides, the value of x cannot equal 2. You're going to notice that we have a vertical asymptote at x equals 2. Okay, and our horizontal asymptote is still at y equals 0. That's because we notice that there's nothing extra. We'll see more where we have different horizontal asymptotes. Okay, so we're going to go ahead and graph this. We're going to identify the asymptotes and then graph the following function, y equals 4 over the quantity x minus 3. So the first thing you want to notice is what's going to make that denominator equal 0. So if you have x minus 3, we know that cannot equal 0. If we add 3 to both sides, we realize that the value of x cannot equal 3. When I'm drawing my asymptotes, I typically like to just draw a vertical dashed line at x equals 3 because I know that when I'm sketching my graph that it's never going to hit that. And because we don't have anything extra at the outside here, like plus or minus some extra number, Our horizontal asymptote is just going to be here at y equals 0. So I'll write the asymptotes are at x equals 3 and at y equals 0. And then we're going to try to graph this, so we might want a couple nice convenient points. For here, I'm going to choose x. When I make my table of values, I'll go ahead and do x equals 4, x equals 5, because it looks like I can do those on my graph. So then if I'm plugging that in, 4 over 4 minus 3, that's 4 over 1, which equals 4. And then 4 over 5 minus 3 is going to be 4 over 2, which equals 2. So I'll graph those two. I've got 4, 4, 5, 2. And because this is a rational function graph, they're all going to follow the same basic curve. And then it would be probably smart of me to get some points on this other side. So I'm going to choose like 2 and 1. And I've got 4 over 2 minus 3. So that's 4 over negative 1 is negative 4. And then 4 over 1 minus 3, 4 over negative 2, it's negative 2. So I'll plot these points. 2, negative 4, 1, negative 2. And again, I'm going to draw that smooth curve that will connect the lines. This looks like a rational function graph, and I've stuck away from touching the asymptotes. Okay, this one has a plus or minus here, so it's going to have a horizontal asymptote that's not at y equals 0. So when I'm finding the asymptotes again, the first thing you always look at is what makes that denominator equal 0? So we don't want x plus 4 to equal 0. So the thing that makes that happen is when x equals negative 4. So we know x cannot equal negative 4. So I like to go ahead, just like I said before, draw that vertical asymptote. And then typically, if it was just this, we'd have a horizontal asymptote right at y equals 0. But this shifts our graph up 3 units. So that's going to make my horizontal asymptote at y equals 3. And my vertical one was at x equals negative 4. These are my asymptotes. So I'm going to go ahead and do that. Draw y equals 3. And dash that. It's not actually part of my graph. I just know I don't want to hit that line. Then I'm going to go ahead and graph some points. Maybe again, you're just going to plug and chug some values that make it convenient and make a smooth curve. So go ahead and try that without me, and then I'll show you the answer. Created my table of values here on the left, and then I plotted my points with a smooth curve, and voila, there you go, and it has the same shape once again. So we've talked about a lot of families of functions this year. We started out with linear functions, y equals mx plus b, and getting that straight line. We've done a lot of work with quadratic functions, those parabolas. We did absolute value functions that made that V curve. Exponential functions that started out shallow usually and then increased more and more rapidly, or sometimes they were decreasing as well. Square root functions, which remember you had to be very careful about the domain there because not all values were going to work. It made this nice upward curve. And now rational functions, which look like this. So we're going to be looking just at a lot of examples of graphs and just equations. And I want you to think about what type of family they fit into and then what's their graph going to look like. So I would like you to think about this before I say the answers. Try to pause, try to figure out what the graph looks like, and then see if you agree with me and if you got all the key details about this. Okay, so the first graph, y equals x over 6. It's possibly a bit tempting to think this is the graph of a rational function, but this, if you actually kind of manipulate this a little bit, you'll see it as y equals 1/6 x. So you could hopefully tell that this is actually going to be a linear function with the slope of 1/6 and a y-intercept of 0. Okay, so it would look kind of like that if you're just thinking about what the graph would look like. Second example, y equals 6 to the power of x. Try to think what type of function that is and also identify some key features. Okay, This is an exponential graph, and if you kind of plug in x equals 0 here, you're going to get that it starts at 1. A lot of times we think that his initial value is 1. You could have some negative exponents as well where it's going to be less, but we'd say kind of the y-intercept, I guess maybe is a better way to say this. The y-intercept is 1, and the growth factor is 6, so it's going to go up steeper and steeper and steeper and steeper. Okay, this third graph that we're going to look at is y equals 6x squared. We spent a lot of time on quadratics, so I want you to tell me a lot about this graph. Okay. So you should have pointed out that this is going to be a quadratic function. I wanted you to notice it's a parabola. It's going to open upward. It's going to be pretty narrow. The vertex is going to be at 0, 0. So your graph would look sort of like that. Those would be the key features. And then we're going to look at 3 more types. Okay, now we see y equals the absolute value of x minus 6. So think about what that would do and how it's different from the parent function as well. This is actually an absolute value graph, and it's going to be a V shape. It's going to open upward. Its vertex is at 6, 0 because that x minus 6 that's inside the absolute value is going to shift the graph 6 units to the right of just the parent function y equals absolute value of x. So when you graph this, it's going to look sort of like, starts over here at 6, 0 and opens up. Okay. The next one, y equals 6 divided by x. Think about what that will look like. This is actually a rational function, like the type we did today. So, and it's also a special type in inverse variation, just because it has the 6 and then the y and the x and no extra added. It's in the form y equals k over x. It's going to have asymptotes at x equals 0 and y equals 0. So when you graph that, it's going to look pretty much like the parent function, but just a little steeper because of that 6 instead of a 1. Okay, and then the last one we're going to look at, y equals the absolute, not the absolute value. That's a tendency I say instead of radical for some reason. Y equals the square root of the quantity x minus 6. When we're looking at that, that's going to be a square root function or a radical function. So we'll have this same general shape, but because this x minus 6 is under the radical, again, it's going to shift it 6 units to the right. Its domain has to be greater than or equal to 6. So it's going to come over here, x equals 6, kind of make this graph. Okay, so I want you to be able to graph absolute value functions, radical functions, rational functions, parabolas. We're doing linear graphs. All these types of graphs, you can do all of them with a table of values, but think about making it easier for yourself. Okay, and I'll see you in class.